Linear Algebra II, Lecture 11, Distance, Orthogonal Matrices, and Isometries. Let us recall the orthogonal decomposition which we had during the previous lecture. Let E be an Euclidean space with a fixed inner product. Let V in E be a subspace. Then we can consider the orthogonal complement V orthogonal of V in E. By definition, the orthogonal complement consists of all vectors W in E which are orthogonal to all vectors in V. In other words, W belongs to the orthogonal complement if and only if the scalar product between W and any vector V in V is 0. And the orthogonal decomposition was the claim that any element U in our Euclidean space can be uniquely written as a sum of two elements V and W, where V is an element in V and W is an element of the orthogonal complement to V. The element V was called the orthogonal projection of the element U onto V. And similarly, the element W is the orthogonal projection of U onto the orthogonal complement of V. It is very useful to note the following, that the orthogonal complement to the orthogonal complement of V is equal to V. To prove this, we first note that directly from the definition, it follows that V is a part of the second orthogonal complement of V, because by definition, every element in V is orthogonal to every element in the orthogonal complement to V. And now the equality that V coincides with the second orthogonal complement follows directly from the dimension count. That we have seen that the dimension of the whole Euclidean space is equal to the sum of the dimensions of V and the dimension of the orthogonal complement. So V cannot be smaller than the double orthogonal complement. Now let us move towards the notion of a distance between a vector and a subspace in an Euclidean space. Consider the orthogonal decomposition U is equal to V plus W of some element U in our Euclidean space. So here V is an element in V and W is an element in the orthogonal complement to V. The claim is that for any element X in V, the length of the element U minus X is greater than or equal to the length of the element U minus V, which is equal to the length of W. So here the second equality, that the length of U minus V is equal to the length of W, this is trivial because W is equal to U minus V. So the content of the lemma is really to prove the inequality here. So now let us use this orthogonal decomposition to write the element U minus X in the form V minus X plus W. So here we see that U is equal to V plus W, and then we subtract X, and let's arrange it so that we subtract it from V. Now note that V minus X belongs to V, because both V and X belong to V by assumptions, and W is an element of the orthogonal complement. So the vector V minus X is orthogonal to the vector W. In other words, the length of the vector U minus X squared is equal to the sum of squares of the lengths of the vector V minus X and W. This is because V minus X and W are orthogonal to each other. Consequently, the length of U minus X squared is greater than or equal to the length of W squared, because the length of V minus X squared is a non-negative real number. And now if we take the square root, and we know that lengths are positive, so we get the inequality that the length of U minus X is greater than or equal to the length of W. And this is exactly as claimed. So now we can define the distance from a vector to a subspace. Again, consider an element U in E and its orthogonal decomposition into the sum of V and W, where V is in V and W is in the orthogonal complement to V. Definition: the length of the element W is called the distance from the vector U to the subspace V. And this is motivated by the previous lemma, by the inequality, that the distance between U and any other element in V is greater than or equal to than the length of W. And the length of W, this distance, is achieved for x is equal to V. And here is the illustration, just by picture, of this thing. So assume that the horizontal line is our subspace V, and the vertical line is our subspace V orthogonal complement. So here we have a vector U in E, some arbitrary vector, and we write it as a sum of the vector V from V and the vector W from the orthogonal complement. And now if we take any vector x in V and look at the difference, so here is the vector V minus x, then we have here this triangle where this angle is 90 degrees. And this means that the side U minus x of this triangle is at least as long as the side W of this triangle. So this is the illustration of the lemma, and this is a justification why the length of W is called the distance from U to V. So here is an example. So let V be the subspace of E4 generated by the following three vectors. The vector V1, which is 1, 0, 1, 0, the vector V2, which is 1, 1, 1, 1, and the vector V3, which is 1, minus 1, 1, minus 1. Let us determine the orthogonal projection of the first basis vector E1 from the standard basis onto this subspace V, and also the distance between this vector E1 and V. So here's the solution to this example. Our subspace V is generated by three vectors. In order to compute the orthogonal projection of a vector onto a subspace, the best way is to find some orthonormal basis in V. To find an orthonormal basis, we need to start from a basis and then use Gram-Schmidt process. So let us start by determining some basis in V. For this, let us write the generators V1, V2, and V3 of V as columns in a matrix, and we need to reduce this matrix to a row echelon form using Gauss elimination. So here we immediately see that row 3 and row 1 are the same, so we can delete row 3. And also rows 4 and 2 are the same, so we can delete row 4. We end up with this matrix 1, 1, 1, 0, 1, minus 1. In this matrix, the leading elements are in columns 1 and 2, and this means that the vectors V1 and V2 form a basis in V. So now we can use the Gram-Schmidt method to find an orthonormal basis in V. So the first vector, the basis vector W1, is just computed as normalization of V1. So we take V1 and we divide it by its length. So the vector V1 is 1, 0, 1, 0, and we divide it by its length, which is the square root of 1 square plus 0 square plus 1 square plus 0 square. The outcome is 1 divided by the square root of 2 times 1, 0, 1, 0. On the next step of Gram-Schmidt method, we compute the auxiliary vector W2 tilde, which we define as V2, our second vector from our basis, minus the projection of V2 on the subspace generated by W1. So we take V2 and we subtract W1 with the coefficient, the scalar product between V2 and W1. Since W1 is V1 divided by its length, we can rewrite it as V2 minus V1 with the coefficient, the fraction, where the numerator is the scalar product between V2 and V1, and the denominator is the scalar product between V1 and V1. So V2 was the vector 1, 1, 1, 1, V1 was the vector 1, 0, 1, 0. The denominator we computed previously, it's 2, and the numerator we should take the scalar product between these two vectors, so it's 1 plus 0 plus 1 plus 0, so it's also 2. So the answer is that W2 tilde is v2 minus v1, which is a vector 0, 1, 0, 1. And finally, the second vector w2 of our ONB is obtained by taking the vector w2 tilde and dividing it by the square root of the scalar product of w2 tilde with itself. So it should be square root here in the denominator. So we have the vector 0, 1, 0, 1, and we divide it by the square root of 0 square plus 1 square plus 0 square plus 1 square. The outcome is 1 divided by the square root of 2, 0, 1, 0, 1. So now we can compute the projection of the first basis vector e1 onto v. So this is computed. So if we project a vector onto a subspace and we have an ONB in this subspace, the formula is that we should take the linear combination of the elements in our ONB, and the coefficient should be just the corresponding scalar product. So we have W1 with a coefficient, the scalar product between E1 and W1, plus W2 with a coefficient, the scalar product E1 and W2. So since W1 is V1 divided by its length, and W2 is W2 tilde divided by its length, the same thing is V1 with the coefficient, the fraction where the numerator is a scalar product between E1 and V1, and the denominator is a scalar product between V1 and V1, plus W2 tilde, where the coefficient is the fraction with the numerator being the scalar product between E1 and W2 tilde, and the denominator is the scalar product of W2 tilde with itself. So V1 is a vector 1, 0, 1, 0, W2 tilde is a vector 0, 1, 0, 1, and in both cases the denominators are 2. And now if we take E1, which is a vector 1, 0, 0, 0, the scalar product with V1 will be 1 because it's 1 plus 0 plus 0 plus 0, so it's 1. And the scalar product with W2 tilde will be 0 because it's 0 plus 0 plus 0 plus 0. So the second summand disappears, and the first summand just gives 1/2 of 1, 0, 1, 0. So this vector is exactly the orthogonal projection of the vector E1 onto V. The complement to this projection is the element E1 minus the projection, minus 1/2, 1, 0, 1, 0. The answer is the vector 1/2, 0, minus 1/2, 0. And so the distance from E1 to V should be the length of this vector. So the length of this vector is 1/2, the length of the vector 1, 0, minus 1, 0. So this is 1/2 of the square root of 1 square plus 0 square plus minus 1 square plus 0 squared. And the numerator is a square root of 2 and the denominator is 2, so we get 1 divided by the square root of 2. So the distance from E1 to V is equal to 1 divided by the square root of 2. Now let us discuss the transformation matrix between two orthonormal bases. Let E be a Euclidean space, and E, consisting of E1, E2, and so on, Ek, be an orthonormal basis in E. Let H, consisting of H1, H2, and so on, Hk, be another orthonormal basis in E. Let TEH be the transformation matrix from E to H. So the question which we would like to address now is what are the properties of this transformation matrix? One can define the transformation matrix for any pair of bases in any vector space. But now we have not arbitrary bases but orthonormal bases, and so it is natural to expect that transformation matrices between orthonormal bases might have some extra nice properties. So let us recall how the transformation matrix is written. So we take the first element of the second basis, the vector h1, and we take its coordinates with respect to the basis E, with respect to the first basis, and we write the coordinates as the first column. Then the second column consists of the coordinates of h2 with respect to the basis E, and so on. The last column consists of the coordinates of the vector hk with respect to the basis E. Since H is an orthonormal basis, then the inner product between Hi and Hj is by definition delta Ij. And there is another way to write this inner product. The transformation matrix consists of the coordinates of H in an orthonormal basis E. If we have two vectors with coordinates given in an orthonormal basis, the scalar product between them is just the sum of products of the corresponding coordinates. And there is a very nice way to get the sum of products of the coordinates of these HIs. We can take this transformation matrix, takes its transpose. So when we take the transpose, then columns become rows. And then we write transpose on the left. And now if we multiply this transpose with the original transformation matrix, so when we multiply two matrices, the rows of the left matrix are multiplied with columns of the right matrix, as in the standard scalar product. So the outcome will be exactly the matrix of scalar products between the rows of the matrix to the left and the columns of the matrix to the right. But the rows of the matrix to the left are the columns of the matrix to the right, and so what we will end up with is exactly the matrix of the scalar products of HIs and HJs. And because H is an orthonormal basis, this will be the identity matrix. So we have just established the fact that if we take the transformation matrix between two ONBs, and if we multiply it on the left with its transpose, we will get the identity matrix. Matrices with such properties have a special name. They are called orthogonal. Definition: a k times k real matrix is called orthogonal if and only if the product of this matrix with its transpose on the left is equal to the identity matrix. For example, a 1 times 1 matrix consisting of a real number A is orthogonal if and only if A is plus or minus 1. Example 2, the identity matrix is orthogonal directly. From the definition, it coincides with its transpose. So here is the theorem. A k times k matrix is orthogonal if and only if it is the transformation matrix between two orthonormal bases in some Euclidean space of dimension k. Proof. On the previous slide, we already established the if part. Any transformation matrix between two ONBs is an orthogonal matrix. And for the only if part, we have to go back the arguments for the if part. So let A be an orthogonal k times k matrix. Consider the standard Euclidean vector space Ek with a standard basis E. Note that an orthogonal matrix is invertible by definition. Its inverse is its transpose. Any invertible matrix is definitely a transformation matrix between some bases. So there exists a basis H in Ek such that the transformation matrix from E to H is exactly A. To construct basis H, we should treat the columns of A as coordinates of the basis elements in H with respect to the basis E. And now, because of our discussion of what happens if you multiply A with A transposed, the property that A times A transposed is equal to the identity translates exactly into the property that the columns of A are orthonormal to each other with respect to the standard scalar product on Ek. In other words, the basis H is an ONB in Ek. And so we have constructed such a basis H starting from our matrix A, and so we realized our orthogonal matrix as a transformation matrix between two ONBs. And this completes the proof of the theorem. Now let us discuss some properties of orthogonal matrices. Property 1. If A is an orthogonal matrix, then the inverse of A is equal to the transpose of A. This follows directly from the definitions. A is a quadratic matrix such that A transposed A is equal to identity. This implies that A transposed is equal to A inverse. Property 2. If A is orthogonal, then A transpose is also orthogonal. Proof? So since A transpose is A inverse, we can also write that A times A transpose is equal to the identity matrix, and of course A is the double transpose of itself. So A is equal to the transpose of the A transpose. So by definition, the transpose of A is also an orthogonal matrix. Property 3, if A is orthogonal, then A inverse is orthogonal as well. Well, this follows by combining the first two properties. A inverse is equal to A transposed, and A transposed is orthogonal. Property 4, for an K times K matrix A, the following assertions are equivalent. A is orthogonal, columns of A form an orthonormal basis in EK, A transposed is orthogonal, columns of A transposed form an orthonormal basis in EK, and then rows of A form an orthonormal basis in EK. Proof? So the equivalence of 1 and 2 is just a definition, similarly to the equivalence of 3 and 4. The equivalence of 1 and 3 follows from property 2. And now the equivalence of 4 and 5 follows by noting that rows of A are exactly columns of AT. Great. Let us now talk about isometries. Let E be an Euclidean space and F a linear operator on E. Definition: the linear operator F is called an isometry provided that it has the following property. For any element V in E, the length of V is equal to the length of f of V. So F is a linear operator which preserves lengths of all vectors. Here is an example. Any rotation is an isometry. Here is an illustration. If we have a rotation by some angle phi, so if we start with 2 points which we rotate by some angle phi around the origin, then this rotation will not change the distance between these 2 points. Example 2, any reflection is an isometry. So if we have some subspace V in our Euclidean plane, and our linear transformation is a reflection with respect to V, so we take any point, we orthogonally project it on V, and then we go to the other side on the same length. So we use our V as a mirror, and the linear transformation is taking the mirror image. Of course, taking the mirror image does not change the distance between points. Example 3, a negative example. An orthogonal projection is normally not an isometry. So here's the illustration. If we orthogonally project some segment which is not parallel to the subspace on which we project, then of course we change the distance between the original points. The distance between the projecting points will be shorter than the distance between the original points. This is because the original points form a hypotenuse in this right-angled triangle, and the orthogonal projection forms one of the other sides. So let us characterize the isometries in an Euclidean space. Theorem: let F be a linear operator on an Euclidean space E. Then the following assertions are equivalent. Assertion A, F is an isometry. Assertion B, F preserves scalar product in the sense that for any V and W in E, the scalar product between V and W is equal to the scalar product between f of V and f of W. Assertion C, if E is an orthonormal basis in E, then the matrix of F with respect to this basis is orthogonal. Proof. Let us first prove that B implies A. So assume that F preserves the scalar product. Then the length of f of V is defined as a square root of the scalar product of f of V with itself, By b, this is equal to the square root of the scalar product of v with itself, which is by definition the length of v. So property b implies property a. Now let us prove that property a implies property c. And isometry is clearly an invertible map, because the only thing which is sent to 0 is 0, because the length 0 is preserved. So an isometry is invertible, and therefore, if we apply it to an orthonormal basis E1 and so on Ek, we will get a basis in an Euclidean space. So we want to prove that we will get an orthonormal basis. First of all, since f is an isometry, it preserves the lengths of vectors, so all elements of O and B will be sent to vectors of length 1. So the outcome, the basis f of v1 and so on f of ek, will be a normed basis. All basis vectors will have norm 1. If I is not equal to j, then f preserves the length of the vector ei minus ej. So the length of f of ei minus ej is equal to the length of ei minus ej, which is equal to the root of 2. Hence, the sides of the triangle consisting of 0, f of ei, and f of ej are, so the length of f of ei is 1, the length of f of ej is 1, and the length of f of ei minus f of ej is the square root of 2. And now we can consider the following equality. So 2, this is square root of 2 squared, is equal to f of ei minus f of ej, scalar product with itself. Now we can use the bilinearity of the scalar product to rewrite it as the scalar product of f of ei with itself plus the scalar product of f of ej with itself minus twice the scalar product between f of ei, f of ej. So the first summand we know is 1, and the second summand we know is 1, and the third summand is just minus 2 times the scalar product between f of ei and f of ej. So 2 is equal to 1 plus 1 minus something. It follows that the scalar product between f of ei and f of ej is equal to 0. So this means that any pair of different vectors in our basis is orthogonal. So this basis is an orthonormal basis. And this means exactly that the transformation matrix from E to the basis f of v1 and so on f of ek, which coincides with the matrix of f with respect to the basis E, that this matrix is orthogonal. Finally, let us prove that C implies B. So assume that the matrix of f with respect to E is orthogonal. Let x and y be two elements in E. Then, the scalar product between f of x and f of y is equal, by definition, to the product between the vector of the coordinates of f of y with respect to the orthonormal basis E and the transpose of the vector of the coordinates of f of x with respect to the O and B E. Now we can use that the coordinates of f of y are equal to the matrix of f times the coordinates of E, and similarly for x. But since we have here the transposed, we have to swap the sides and take the transposed, so we have the following expression. The coordinates of x in E transposed times the matrix of f with respect to E transposed times the matrix of f with respect to E times the coordinates of y with respect to E. Now we have assumed that the matrix of f with respect to E is orthogonal, so it times with its transposed on the left is the identity matrix. So this expression is equal to the expression obtained by taking the coordinates of x with respect to E transposed and times the coordinates of y with respect to E, and that's it. And this expression is exactly the scalar product between x and y. And this proves part B. Let us conclude by solving the following problem. Determine the matrix in the standard basis of the orthogonal projection onto the subspace V in E4, generated by the vectors V1, which is 1, 0, 0, 1, V2, which is 2, 1, 1, 0, and V3, which is 3, 1, 1, 1. Solution. So we want to compute orthogonal projections of all standard basis vectors on V, so we need an orthonormal basis in V. Let us start by finding some basis in V. So we write the coordinates of our three vectors as columns in the matrix, and we reduce this matrix to a row echelon form using Gauss elimination. So the matrix is 1, 2, 3, 0, 1, 1, 0, 1, 1, 1, 0, 1. So we use this one to eliminate this one. So we subtract row 1 from row 4. So rows 1, 2, and 3 remain the same, and row 4 becomes 1 minus 1 is 0, 0 minus 2 is minus 2, 1 minus 3 is minus 2. And now we see that rows 2 and 3 coincide, and row 4 is linearly dependent with them. So we can throw away rows 3 and 4 to get the matrix 1, 2, 3, 0, 1, 1. So in this matrix, the leading elements are in columns 1 and 2, which means that the elements V1 and V2 form a basis in V. So now let us apply Gram-Schmidt method to V1 and V2. By Gram-Schmidt method, W1 is equal to the normalization of V1. So V1 is a vector 1, 0, 1, 0. So we should take it and divide by its length, which is the square root of 1 squared plus 0 squared plus 0 squared plus 1 squared. We get 1 divided by the square root of 2 of the vector 1, 0, 0, 1. Next step, the auxiliary vector W2 tilde is equal to V2 minus W1 with the coefficient V2 scalar product with W1. So since W1 is V1 divided by its length, we can rewrite it as V2 minus V1 with the coefficient, the fraction where the numerator is the scalar product between V2 and V1, and the denominator is the scalar product between V1 and V1. So the vector V2 is 2, 1, 1, 0. The vector V1 is 1, 0, 0, 1. The scalar product between V1 and itself is 2, and the scalar product between these two vectors is 2 plus 0 plus 0 plus 0. It's 2 as well. So the coefficient here is just 1, so we get V2 minus V1, and this is equal to 1, 1, 1, minus 1. Finally, we take this vector W2 tilde and divide by its length. So it should be the square root of W2 tilde with itself. So this gives us 1, 1, 1, minus 1 divided by the square root of 1 squared plus 1 squared plus 1 squared plus minus 1 squared. This is the square root of 4, which is 2. So the vector W2 is equal to 1/2 times 1, 1, 1, minus 1. Conclusion, the vectors W1 and W2 form an ONB in V. So now we use the formula that the projection onto V of any vector x is equal to the following linear combination. So we take W1 with the coefficient, the scalar product between x and W1, and we add W2 with the coefficient, the scalar product between x and W2. Since we know that W1 is V1 divided by its length, and W2 is W2 tilde divided by its length, we can rewrite it as V1 with the coefficient, the scalar product between x and V1, divided by the scalar product between V1 and V1, plus W2 tilde with the coefficient, the fraction where the numerator is the scalar product of x and W2 tilde, and the denominator is the scalar product between W2 tilde and W2 tilde. So in order to write the matrix of the projection, we need to compute the images of all elements in the standard basis for this projection. So we need the projections on V of all EIs where I is 1, 2, 3, and 4. So let's do the projection of E1. So the scalar product between E1 and the vector 1, 0, 0, 1 is 1. The scalar product between E1 and the vector 1, 1, 1, minus 1 is 1. So the numerators are 1 here and 1 here. The denominators we know it's 2 for V1 and 4 for W2 tilde. So this is the outcome which we can now compute. So this is 1 divided by 4 We have 2 plus 1, 3 here, 1 and 1 here, and 2 minus 1, which is 1 here. So the projection of E1 is 1 divided by 4 times 3, 1, 1, 1. The projection of E2, the numerators are 0 because we have 0 here and 1 here. So the first sum disappears and we just get 1 divided by 4 times 1, 1, 1 minus 1. The projection of E3 is similar. We have, because of the 0, we have 0 here, and because of this 1, we have 1 here. So we again get 1 divided by 4 times 1, 1, 1 minus 1. And finally, the projection of E4. So the scalar product here is 1, and here it is minus 1. So we have 1/2 of 1, 0, 0, 1 minus 1/4 of 1, 1, 1 minus 1. So we will have 1 divided by 4 times 2 minus 1 is 1. Then we have minus 1 from here. And we have 2 plus 1 is 3. Putting all this together, the projection on V, the matrix of this map, in the standard basis is 1 divided by 4 times the matrix 3, 1, 1, 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, minus 1, minus 1, 3. Here are some further problems and questions. Question 1. Prove with all details that the product of the transformation matrix from E to H times its transpose on the left is the identity matrix if the transformation matrix is a transformation matrix between two ONBs. Question 2. Describe all diagonal orthogonal matrices. Question 3. Prove that the product of two orthogonal matrices is an orthogonal matrix. Question 4. Sometimes, but very rarely, an orthogonal projection can be an isometry. When exactly can such a thing happen? Question 5. Determine the matrix in the standard basis of the orthogonal projection onto the subspace V generated by the polynomials 1 plus x, x plus x squared, and 1 plus 2x plus x squared in the Euclidean space of all polynomials of degree at most 2 with respect to the scalar product given by the integral from 0 to 1 f of x, g of x, dx. Thank you very much and see you next time.